Alrighty, hello everyone. In this video we're going to be talking about elimination reactions. So in our last chapter we talked about substitution reactions. So we saw that if we have a molecule that has a good leaving group and we react that molecule with a nucleophile such as sodium hydroxide, that the reaction will undergo an SN2 mechanism where the nucleophile, now the alcohol group, is going to replace the bromine. Right? And we also saw that there was an inversion of configuration because it's a backside attack, or in the case of a cyclic molecule, it's a top phase attack. And then we end up getting an alcohol group. Well, in today's video, what we're going to be looking at is elimination reaction. In the case of a substitution reaction, what is happening is one functional group is being substituted in for another functional group, right? So it's what we call a substitution reactions, and we saw that it's either an SN1 or an SN2, and if we're using a strong nucleophile and we have a secondary alkyl halide, then it would be much like an SN2 mechanism. Well, in elimination reactions, we're eliminating two groups across a carbon-carbon bond, and the idea is that we're forming a pi bond. Okay, so, and we'll notice that elimination reactions are favored at higher temperature. So we'll use delta for heat or temperature to indicate that it's an elevated temperature. And alcohol groups are not very good leaving groups. So what we typically do is protonate it. So if we use concentrated acid, right, and we'll just write hydronium ion in this case, it would actually favor elimination. And we're eliminating two groups, right? And that's what we're going to be looking at in today's video, right? Elimination, where we're getting rid of two groups across a carbon-carbon bond, right? So this was substitution, and in this case, what we looked at is elimination, right? You're eliminating two things. So one was an alcohol group. What must have the other one been? If you're forming a pi bond, you must have eliminated something off of that carbon, which was a hydrogen, but it's really a proton. So we're going to look at elimination reactions, and we're going to notice how similar some of the reagents are, because some bases can also be, or some nucleophiles can also act as bases. So we're really going to look at elimination reactions. Okay. And what is happening is two things. We're eliminating two groups, right? You're eliminating, you're going to eliminate two groups across a carbon-carbon bond, right? To form a new pi bond, they have to be across a carbon-carbon bond. Two groups across a carbon-carbon bond, right? It has to be across a carbon-carbon bond. Well, what are those two groups? Those two groups are a leaving group, has to be a good leaving group, halogens or alcohol if you protonate it, and a proton, right? What we're eliminating is a hydrogen without its one and only electron. So we're eliminating a leaving group and a proton. Well, what happens in elimination reactions, or one type of elimination reaction, is that a new pi bond is formed, right? A new pi bond is formed, right? And that we're going to be looking at those mechanisms. The mechanisms are somewhat similar to SN1 and SN2, but we're going to be looking at two different mechanisms, and we'll call them E1 and E2. All right, but before we talk about the different mechanisms, let's look at those two factors. That the fact that we're eliminating two groups, that one is a leaving group and one is a proton, and that we're forming a pi bond. So suppose this is what you have. Okay. Well, if we're eliminating a proton, to take away a proton, what would you need? In acid-base reactions, what would deprotonate an acid? A base, right? So you'll notice that the reagent is actually a base. right? And we could just use the symbol B with a negative charge to indicate that it's a base. That's our reagent. So in an elimination reaction, the reagent is a base. Right? That's just the symbol we use for it, like nucleophile, electrophiles, and then the base is the B with a negative charge. Okay, so here's our starting material. We have a base, right? So we have a leaving group, right? So what we do is we look at the carbon directly attached to the leaving group, and we call that the alpha carbon, right? We call that the alpha carbon, right? The carbon directly attached to the leaving group is the alpha carbon. Well, when a pi bond is formed, or a double bond, basically in this case, we have one sigma bond and one pi bond, so we have a double bond. That double bond formed at the carbon that was directly attached to the leaving group and one bond away, right? So, okay, so the carbon that's directly attached to the leaving group in general is known as the alpha carbon. So this is an example of an alpha carbon. This is an example of an alpha carbon. So in an elimination reaction, the proton that is eliminated from a carbon one bond away, but that carbon has to have a proton or a hydrogen attached to it. And we call those carbons the beta carbons. Right? So those are examples of beta carbons. Okay, so the product that forms is always between the alpha carbon and a beta carbon, unless it goes through some rearrangement, which we talk about on a later chapter. All right. So a pi bond could form right there, right? This was the carbon attached to the leaving group. I'll just make it into a dot. Or it could be between this carbon and that carbon. So you could have a carbon-carbon double bond between those two carbons, right? How could you compare this alkene to that alkene? Okay, let's take a look at substituted alkene. If you have a carbon-carbon double bond, right? That's not substituted, it's just an alkene. If you have one bond attached to it, that's monosubstituted alkene. Right? If you have two bonds attached to it, doesn't matter what this group is attached to, it could be a longer carbon chain. You have a di-substituted alkene. That di-substituted alkene could either be cis or trans. Remember, it has to go through to a chemical reaction to convert through a trans or a cis alkene, right? It can't be through a simple rotation because we can't rotate through a carbon-carbon double bond, but we could simply rotate across a carbon-carbon single bond. So those are di-substituted. We can have a tri-substituted alkene. We can have a tetra-substituted alkene. Well, the more the substituted the alkene, the more stable it is, right? More stable. Okay. So and then when we think about elimination reactions and we get two products, one will end up being the major product and one will end up being the minor product. The product that has a higher percent in solution would be the major product, and that really depends on the base, right? So we're going to look at those in a minute. All right, so let's think about bases. What can you think of and correlate it to a base? Water, right? Water. We know water is a base, right? It can act as an acid or a base, so we could think about water as a base. Bases are electron pair donors, so they'd have to have a lone pair of electron. In fact, anything with an OH could be a base. You could have water. You could have methanol. This is really a carbon, so this is methanol. You could have ethanol. And we can abbreviate methanol as Me for the methyl group, and then OH, that's methanol as well. It could be ethanol, where we have OH and ET, or you could think about it as being, that's ethanol, right? That Me comes from the methyl group. that ET comes from the ethanol group. All right, we're going to learn about naming alcohol in a different chapter. So those are examples of bases. When we talked about substitution reactions, you know, an oxygen and OH group, those were examples of nucleophiles as well. So any base that basically has the HOR, right, where R is whatever group, it could be a hydrogen or an alkyl group, those are bases. Those are examples of bases and nucleophiles as well. So the product could both be a substitution and an elimination reactions. And we called those weak bases, right? And similar to those weak bases, we had the strong bases, where you had sodium instead. And what made it strong versus weak is that now the oxygen is actually charged because you have an ionic bond. What we have in here really is a sodium that is positively charged and the oxygen that is negatively charged. So we could have sodium hydroxide, we could have sodium methoxide, or we could have sodium ethoxide. Those are all examples of strong bases. Okay, so those bases overall, if you think about their structure, they're not bulky bases. If you want to think about what a bulky versus not bulky is, you could think about monosubstituted to tetrasubstituted alkene. This would be considered more bulky of a group. Well, some bases are bulky bases, and those would dictate if something forms a less substituted alkene or a more substituted alkene. So we're going to learn about two new reagents that are bases, but they're bulky bases, right? One is known as tert-butoxide. You have the oxygen with a negative charge, and then you have the potassium that is positively charged. So that's an example of a strong base, but it's a bulky base, all right? It is tert-butoxide, but it's really potassium tert-butoxide. I'm just gonna potassium tert-butoxide, right? That K is, you can write, actually, let me just write it out for you. Right, you have potassium tert-butoxide. So it's a strong base, but it's a bulky base, right? Do you have any weak bases that are bulky bases? Yes, we do. Triethylamine is an example of a bulky base, right? You have 3 ethyl groups, right? It is known as a triethylamine, right? Well, those are 2 examples of bulky bases that you'll need to know, and they favor the formation of a less substituted alkene, right? Well, there is a term that we use for that. The less substituted the alkene is known as the Hofmann product. Right? The more the substituted the alkene is known as the Zaitsev product, okay? So when a reaction takes place, when an elimination reaction takes place, we get a mixture of 2 products. And the one that ends up being the major product depends on which base we use. So if potassium tert-butoxide was the base, then the Hofmann product would predominate. If water was the base, then the Zaitsev product would predominate. If any of sodium ethoxide, ethoxide, or hydroxide was a base, again, the Zaitsev product would predominate, right? But in solution, we get a mixture, right? But one will predominate, and we call that the major product. All right, so if we use triethylamine, a bulky base, or if we use potassium tert-butoxide, which again is a bulky base, bulky bases favor the Hofmann product. Okay, so now let's take a look at the actual mechanism. What would the mechanism look like, right? Well, when we think about the mechanism, we again have to look at the alpha carbon, and we have to look at the 2 beta carbons, all right? Those beta carbons, bases deprotonate a proton. So that beta carbon would have to have a hydrogen attached to it, which we refer to as the beta hydrogen. Now, this carbon has 3 more hydrogens, but I'm only drawing 1, right? Okay, so the base is going to deprotonate a beta proton. So there's 2 different mechanisms that we're going to look at. I'm just going to draw all 3 hydrogens so you don't get confused, right? But we only need to deprotonate 1. So now we're actually going to look at the 2 different types of mechanisms, right? We have an E2 mechanism. All right. And in an E2 mechanism, it's elimination by molecular, all right? So both steps are happening at, all the steps are happening at the same time. It's a concerted mechanism, right? Everything happens at once. So if you take a look at that same example that we have up here, we have bromine. Elimination would still require a good leaving group, so we have bromine. We're going to use a base, but let's just use something like sodium hydroxide. Right, so suppose sodium hydroxide is our reagent. We know the alcohol group is negatively charged and the sodium is positively charged, right? We have an ionic bond. In an E2 mechanism, everything is happening at the same time. Sodium hydroxide is not a bulky base, right? So it's going to favor the Zaitsev product, the more substituted alkene. So we take a look at where the leaving group is. That's the alpha carbon. And we look 1 bond away. Does this carbon have a hydrogen? It does. Okay, does this carbon have a hydrogen? It does. If the base eliminates this hydrogen, a pi bond will form right there. If the base eliminates this hydrogen, a pi bond will form right there. Those are the 2 products. But because we're not using a bulky base, it will favor the more substituted the alkene. And if we're drawing the mechanism, you'd want to draw in the hydrogens because we don't, you know, when we do a line bond, we don't draw hydrogens attached to carbon. So if you're drawing the mechanism, you have to draw the hydrogen in yourself. So the base is going to go in and it's going to take a proton. It's taking it as a proton without its one and only electron. Okay? And there's a loss of a leaving group. Well, how exactly does this particular pi bond forms? Well, if the base is taking the hydrogen without its electron, those 2 electrons will actually go in right here to form the pi bond. And if you think about it, if you have a loss of a leaving group right here, that would create a carbocation, right? So those 2 lone pairs of electron would go in to form the pi bond. And then we would get our product where we now have a pi bond right here. Okay, so that's an example of an E2 mechanism. So now let's consider an E1 mechanism. See. All right. And then we'll talk about some reaction specificities that we need to keep in mind, right? Okay, so now let's think about an E1 mechanism. So an E1 mechanism favors weaker bases, right? And it's a stepwise mechanism, right? Stepwise. It's a stepwise mechanism, so it's happening 1 step at a time, much like an SN1. So we're still going to use the same example. Okay, but I'm going to use a weaker nucleophile. I'm going to use water. Okay, so what would be the very first step? So if you take a look at what's happening, those 3 arrows, what we have is a proton transfer. We have the loss of a leaving group. And right here we have a pi bond that forms, right? Those are the 3 things that take place. So now if it's happening stepwise, what would you expect to happen first? A pi bond forms, the proton transfers, or you lose a leaving group, right? You lose a leaving group, so you could create that carbocation. So we have the loss of a leaving group as the first step. So now bromine is gone, right? By the way, and when we talk about substitution, our nucleophiles can be halogen, right? Halogens are only nucleophiles. They are not bases, right? For bases, they're attached to an oxygen, right? You have, in general, form for the base is HOR or NaOR. Halogens are only nucleophiles. Okay, so we have a loss of a leaving group. Now what happens is this carbon now lacks an electron because bromine took both electrons, so you form a carbocation. Okay, well the other two steps are a proton transfer and a pi bond. Okay, so we're using a weaker nucleophile, right? So it's going to favor the more substituted the alkene. So here's a proton. So what happens is that our base, which is water, is going to go in and it's going to deprotonate. So it's taking the hydrogen without its electron. It's taking a proton. But there are two electrons right here that will go in to form a pi bond because that carbon is missing an electron. It's a carbocation. That arrow does not go to the carbocation. It goes to the bond, okay, because it's forming a pi bond. And then we get a pi bond. Now what you have in solution is both products, right? I just drew the mechanism for the major product, right? What you have is both products in this case, but we would call that the major product, or really the Zaitsev product in this case, and this one is our minor product, right? Those are our two products that form. This is just a plus sign. Okay, something to keep in mind in terms of elimination is that it requires heat. Anytime at elevated temperature, it would favor elimination over substitution reactions. So now let's think about the substrate itself, right? Let's think about the substrates for E1 versus for SN1. All right, E1 goes through a carbocation, right? Right, the substrate is our starting material. So let's think of E1 versus of E2. E1 goes through a carbocation when we know primary carbocations are not stable. So it really favors secondary or tertiary substrates, okay? Whereas in E2, when we did SN2, the nucleophilic attack happens at the carbon directly attached to the leaving group. But when we're doing elimination, it is deprotonating a hydrogen one bond away. So the steric interactions become less of a problem. So it actually goes with primary, secondary, or tertiary. In fact, it's actually favored for tertiary. The overall energy of activation for a tertiary substrate is lower, so it's favored, right? The tertiary is also favored for an E1 reaction because of a tertiary carbocation is more stable. So that's the substrate. We could think about our reagent. Now, our reagent is no longer a nucleophile, it's a base, but bases can also be nucleophiles, right? So we could just think about the general formula HOR, right? Where R could be a hydrogen, like water, or an alkyl group. And in an E2, it's attached to sodium, so it's a strong base, right? So the reagent are really bases. Now, there are some molecules that are only bases, all right? They're not nucleophiles. And we're going to talk about two. We're going to consider two that are only bases, right? So if something is only a base, it must be a strong base, all right? So the ones that are only bases are actually strong bases. Sodium hydride is one. And sodium amide is another. Those are only bases, they're strong bases, They favor E2 mechanisms, not E1, right? They do not undergo substitution reactions either. What is the base? In this case, the base is a hydride. In this case, the base is an amide. Right? This nitrogen has 2 lone pairs of electrons. All right, so those are only bases. Or we could have a bulky base. Now, if we have a bulky base, it would favor the less substituted alkene. And we call those regioselectivity. They favor the less substituted alkene, or the Hofmann product, right? And if we're not using a bulky base, it favors the substituted alkene, or the Zaitsev product. All right, so when we talked about SN2 and SN1, we mentioned about stereospecificity, right? Think about the stereochemistry, the overall arrangement of the molecule being an R and S configuration. Okay, well, in E2 mechanism, we don't really have a chiral center, but because we can't rotate around a carbon-carbon double bond, we could think about the stereospecificity in a different term. The idea of having that particular proton and the leaving group being opposite end of one another, what we call an anti-periplanar, right? You could think about it as being trans. However, if what we have is a carbon-carbon single bond, we could easily rotate around a carbon-carbon single bond. So that same molecule, we could move the methyl on top or at the bottom, because it's a simple rotation around this bond. So that anti-periplanar or trans rule does not apply for, a bond that is a single bond, because we could simply rotate. However, you can't rotate this bond to make it look like this. That cannot be a bond rotation, because you cannot rotate around a pi bond, but you can rotate around a single bond. So that anti-periplanar rule does not apply. So when exactly does it apply? It applies when we're dealing with cyclic molecules, right? So I'm going to erase this. All right. Okay, so if we have a bromine, can we rotate around a cyclohexane? No. It could have a chair conformation, a half chair, a boat conformation, but you can't really rotate, right? So suppose you have a methyl right here. Okay, and suppose you have a methyl right here. Well, for the reaction, for an elimination reaction to take place, specifically an E2 mechanism, that does not apply to an E1 because it goes through a carbocation, but it applies to an E2, that the hydrogen on a beta carbon to the leaving group has to be trans to the leaving group, right? Okay, so if we have a methyl right here on a wedge, that means we have a hydrogen on a dash. If we have a methyl here on a dash, it means we have a hydrogen on a wedge, right? If you take a look at those two, the hydrogen and the bromine, they're cis to one another, they're the same. If you take a look to this bromine or in this hydrogen, they're trans to one another, right? So that's the only one where elimination via an E2 mechanism can actually take place, all right? And if you draw it in a chair conformation, it means they're both axial or both equatorial, right? But in this case, one is a dash and one is a wedge, so we have a trans. So that's the only possible position. Despite the fact that you have a proton right here, it is not trans to the leaving group, right? And trans, if you're looking at a cyclohexane, a substituted cyclohexane, one is a dash and one is a wedge. If you're looking at a chair conformation, they're both axial or both equatorial. So now suppose we use something like sodium amide, right? So now this amide carries a negative charge, sodium carries a positive charge. It will go in, it will deprotonate, we have the loss of a leaving group, and we have a pi bond that formed. That would be the mechanism. So now, whatever bond had the carbon, had the leaving group is gone. And one bond away is where the pi bond formed. Okay, we still have a methyl, so we still draw that methyl. But once you have pi bonds, you no longer have molecules on dashes and wedges. So those atoms directly off of the pi bond are now in plane. They could be cis, they could be trans, but they're all in plane. Right? So that's the new pi bond. And we still had a methyl right here. Okay, we still have a methyl right here. That methyl was on a wedge. It's not affected, so it stays on a wedge. Okay, so that's another rule for E2 mechanism, is that they have to be trans to one another. And we call that stereospecificity. Regioselectivity has to do with the Hofmann and the Zaitsev product. That has to do with the stereochemistry of the substrate, so we call that stereospecificity. Stereospecificity, right? Has to do with the stereochemistry of the initial substrate. So it has to be anti-paraplanar. Only applies when you have a cyclic molecule or across a pi bond, not for a carbon-carbon single bond. Okay. So what if our leaving group is an alcohol? We would simply protonate it, right? So we're going to look at a different example using acetic acid, common reagent used. So suppose you have an alcohol group, okay? What we use as a reagent is sulfuric acid, H2SO4, and water, right? And in the presence of heat, that tells us it favors elimination. If we were to draw the mechanism, the very first step would be to make the alcohol group into a better leaving group. And if you recall how to draw sulfuric acid, you have a sulfur double bonded to oxygens, you have an OH group, and you have an OH group as well. The oxygen is acting as a base, it's deprotonating sulfuric acid, those electrons are going to the oxygen, and then we end up forming water, which is now positively charged. It's an excellent leaving group. That's an E1 mechanism. We're using weaker nucleophile. So we have the loss of a leaving group, right? And now we have a carbocation. And then we can have the elimination reaction. Now we could draw the proton. You could use water or the conjugate base of sulfuric acid, HSO4 minus. The pi bond is formed, and then we form our final product. Right? The other products forms, but the Zaitsev product is the major product. Right, if you take a minute and think of this, if you have H2SO4, which is sulfuric acid, it has a pKa lower than 0. It's a very strong acid. And you put it in water, okay? What happens is that you'll form hydronium ion, and the conjugate base of sulfuric acid. Well, any time you put a strong acid in water, the strongest acid now in solution is hydronium ion. So equilibrium will favor somewhat of the reverse direction, right? So we could use its conjugate base to deprotonate. So instead, sometimes, instead of seeing sulfuric acid and water as the reagent, what you'll notice that it says is hydronium ion, right? Because if we put sulfuric acid in water, what we have is a hydronium ion. They really mean the same thing, whether it says sulfuric acid in water or hydronium ion. So could you have protonated the alcohol using hydronium? Yes. And then deprotonated the proton using water? Yes, absolutely. Either one would be correct. All right, so if we use a concentrated solution of acid, it would favor elimination, right? Okay, so I hope that was helpful. I'll follow up with another video where we'll do some examples from the ones we had in class.